All right. Where we left off Monday morning is where we were talking about different types of neural networks, and we even covered a portion of developing an application utilizing ChatGPT through prompt engineering. Now, today what we're going to do is we're going to do a little bit of a back step. Now that we're understanding how to utilize something like AI, we want to actually ensure that we understand what's happening behind the black door, right? Every time this prompt gets sent to a model, and a model processes our prompts and then returns a response. Well, how does it do that? Now, we're not going to dive into building an entire large language model because that would take us a considerable amount of time. So instead, today we'll be diving into PyTorch. We're actually going to be talking about Jupyter notebooks. We'll start working with a data set, that student performance data set that we saw on Monday. We'll work with that data, kind of see what it looks like to work with data frames. Again, this is more of an introduction. We don't expect mastery over this material. After that, we'll break up our data into training and testing sets. We'll take an hour break, at which point we'll take a look at a couple of videos that will break down neural networks and how they work. And then we'll come back to talking about how to train our model, or what is a model with PyTorch. All right. At this point, does anyone have any questions regarding what will be taught today? Loving the background, Andy. All right. If no one has any questions, then let's go ahead and dive right in. So starting off with what is a tensor or a neuron? Let's go ahead and take a look at this TL draw example that we have here. I tried to draw this out for us on Monday a little bit. Essentially, what we're going to be building today will be a model that takes in a series of inputs, right? Or as we've called before, features. And what we're going to be trying to find is a label that gets broken out into percentages at the end. What we're going to do is as soon as we receive all of our features, we're going to open up our neural network by essentially multiplying those tensors by 2. Well, what is a tensor? A tensor is a multi-dimensional list, basically, that will represent a different series of features. Now, this multi-dimensional list gets installed, or not installed, gets saved inside of each independent tensor. Well, Python already has the ability to work with multi-dimensional lists. So what's the necessity behind something like a tensor? Well, a tensor is a special data set that allows us to do a very complex mathematical operations in a very quick manner, such as adding multidimensional lists to one another without having to write an entire algorithm or multiplying different numbers from one multidimensional list to another. Instead, it does it in a more linear process, and there's actual data structures that have already been built out for us to utilize to make these mathematical operations happen in the background. So again, we'll receive a series of features. We'll multiply it times 2 to allow the features to truly build a relationship to one another. And then afterwards, we'll slowly trickle down into our final output is a total of 4 tensors. Now, when I say slowly trickle down, this example here specifically is showing us how every single neural network, or excuse me, every single neuron or tensor is connected to one another, right? Every new layer that was created is somehow related to the very first neuron. It is also related to the second, and so on. The previous layer gets taken into consideration as each neuron on the next layer is created. Well, that relationship continues to happen as we trickle down in the model. And the way that relationship continues to happen is by something called weights and biases. So the image to look at is going to be that weight, and then that looking glass is more of a bias. Now, the way to think about weights and biases, they're essentially just the rules of the game, saying, hey, this is how much this tensor can actually affect the next layer. So that's our weights. And then our biases is saying, well, typically this is what you lean towards, but because you're always leaning in that specific direction, what we're going to do is we're going to stop you as soon as you pass a specific limit that gets set behind the background by the data set and gets essentially kind of a penalty that says, oh, well, now you're above 5. We're going to subtract 4 and reset you back to 1 so that you're still within your left and right lateral limits. And that relationship continues happening all the way until we get to our activation layer, at which point our activation layer just shows us a simple output matters of percentages telling us which one of these outputs is more than likely to be true, which what we're looking at here is going to be the possibility of A, B, C, or D. And I think we have actually a other possibility for F, but we'll take a look at that here shortly. All right. Now, let's start talking about working with data. What we're going to be working with here is going to be the student performance data set. Let me actually share this link to Kaggle with everybody. I shared it in the Avenger questions. In that link, you can see that it talks about the data set. It gives you a little bit of availability regarding to the different um, features that's going to be available to us. So we can see some student information. That student ID doesn't seem like it's going to be important to us, so we could probably drop that as well. We have some parental involvement. That seems pretty important. Demographic details, study habits, extracurricular activities. Now, if we have the correct amount of time to actually work with this, oh, and here you can see we have 0 through 4, so there's a total of 5 options. Okay, fantastic. Um, if we have the proper amount of time, we would actually build something called a relational map, where essentially we could try to figure out through the data that is provided to us, which one of these columns actually has a strong relationship to the answer and which one of them doesn't. That way we could just drop data that's not necessary to try to come up with the correct answers. All right. Well, now let's start diving into our features here, or actually let's start diving into how to work with this data set. Currently, I have it inside of a CSV file. So what do we think we should utilize whenever I'm working with this data? How can I read this data? Let's hear it, Kevin.
Maybe SQL. I'm not too sure.
Yeah, I could load it into SQL, right? I want to work with it within the context of Python. So I could probably utilize something like CSV dict reader as well. But there's actually something even better for working with data now. What we're going to dive into today is working with pandas. But
But
before we can do that, oh, I see, did I hear something?
oh, I just said I knew it, but I thought my mic was off. My bad.
Oh, perfect. All right. So since we're going to be working with pandas, I'm going to go ahead and activate my virtual environment here. You guys should all already have it activated. All right. Now that I have it activated, I can actually start working with installing pandas and creating a Jupyter notebook to actually work with this content. All right, so first thing first, install pandas. Now, the Jupyter notebook portion is a little bit vital, well, it's quite vital to us whenever we're going to be working here. So it's important for us to work through how we're going to get this Jupyter notebook installed and running in our machine. All right, so the first things first, we're going to go ahead and install Jupyter. Go ahead and share the series of commands as well. All right, you can see that Jupyter Notebooks is actually being created now. Now I'm going to go ahead and also grab the Jupyter Notebook extension so I can go into Jupyter. This is the extension that we're going to want to install. Let me see if I could grab a link to this. All right, so now we have the extension installed. We have Jupyter installed. Now we can actually open up oh, actually, we're missing one more installation here, which is the actual kernel for Jupyter Notebooks. All right. We don't know what Jupyter Notebooks is just yet. I will break down what each one of these installments are actually doing and why we're installing all of this stuff. So we're going to pip install IPY kernel. All right. Finally, we'll go ahead and create a Jupyter Notebook. So I'll go ahead and say touch multi class dot IPYNB. Notice that this isn't just a PY file. This isn't just a JS file. This is IPYNB, which is for Jupyter Notebook. So I'm going to go ahead and run that, and we can see a new file being created called Jupyter Notebook. All right. Now, everything that I installed will allow me to actually run this notebook portion here. We haven't utilized notebooks before. The important thing to utilize about notebooks, or where notebooks even came from, is it comes from the data science community. And the super cool thing about utilizing Jupyter Notebooks is that I can actually run markdown files. So I can say, this is a multi-classification data prep. And what we can do is also add a header saying intro to NNs. And I can save it. All right, I can come down here and click the now I want code. I can even move blocks of code around. Click that check mark and it turns into nice readable information. And here I can actually write in a code block. Oh, I didn't add a code block. Let me add a code block. I can write things like print hello. I can try to execute this information. Now, when I try to execute it, notice that it tells me, hey, you haven't chosen a kernel. I don't know what to do just yet. So I'm going to go ahead and stop this action just to make sure that it doesn't run. And we're going to start talking about what is a kernel. Well, a kernel is essentially just a way for my Jupyter notebooks to interpret code. And we've already been working with kernels every time we utilize our terminal. When I type in Python and I go ahead and execute something like main.py, well, that tells my kernel to execute the file of main.py to read all of that text and interpret it into Python. Well, now I want the same thing to happen with my virtual environment, but I need to find a way to tie these two together. So I'm going to go ahead and run which Python 3. I'm going to copy that path. Again, we're going to run which Python 3. And that should give you the path to the Python 3 inside of your virtual environment. From there, I'm going to click on select kernel. I'm going to click on Python environments. Now, when I check this Python environments, it's giving me a couple of different options here. It doesn't seem like it's giving me the one that I have in my path. So instead, I'm going to create a Python environment, VNV, and there I'm going to enter interpreter path. Finally, I'll paste it and press enter. And now you can see that it's recognizing it as actual Python. All right, again, we'll go ahead and select Python interpreter. From there, if you don't see your virtual environment available, you'll click on create virtual environment, or I think it's create Python virtual environment. And then you'll go ahead and enter interpreter path and paste the path. All right. Everything's good. I have my information. I see this VMV has now been created. I'm actually going to start running everything off of this one instead, just to make sure that I'm utilizing the one that's inside of my file. So I'll run deactivate. Then I'll run source.venv bin activate. And everything should still work perfectly fine here. Just to make sure that I still have pandas, I'll run pip install pandas. Okay, it looks like pandas is being reinstalled, and that's because I'm on a different virtual environment, and that's okay. All right. Well, now let's see what happens when I click this play button. Now, when I click this play button, I'm able to see my output of hello right away down in my Jupyter notebooks. All right, so Jupyter notebooks will allow us to write Markdown at the same time that we're writing Python code. And they'll allow us to even move code blocks or decide at which point each independent code block is going to be executed. Now, that's the benefit behind Jupyter notebooks. At this point, does anyone have any questions regarding Jupyter notebooks? Perfect. If no one has any questions, then let's dive into actually working within the CSV file. So we can see that we were able to print hello. Now I want to actually read my CSV file utilizing pandas. So I'm going to import pandas as PD. Again, this as portion is just saying I'm actually just going to utilize a variable of PD to reference to pandas. And I can confirm that works by running PD dash underscore underscore version. I can execute that block of code by pressing play. It's taking a while to read it. And there we can see that I have pandas version of 2.03. So I'm going to go ahead and add a little bit of markdown here. And I'm going to say, hey, first, confirm pandas is installed with the latest version. And that it can be referenced to with a variable of PD. All right. Now in this next portion, I'm going to actually utilize pandas to generate a data frame of my data and drop columns that may interact with my features. So key things to consider here is we want to get rid of insignificant columns. We want to account for null values because that will actually throw off my data set. And we want to balance our data. Well, what exactly does all that mean, right? Get rid of insignificant columns, account for null values, and balance our data. Let's see how that works. First, let's read our data. Well, let's just create our data frame. I'm going to say data is equal to PD. And this is actually going to be a lot easier than doing the whole with open portion. Instead, I'm just going to say, I want to read a CSV file. And the CSV that I want to read is called student performance data.csv. And that gives me data back. Oh, I can run data here to see that output. And now we can see the entire data frame. And let me actually break this down so we can get a better visual. Now we can see the entire data frame of our CSV file. It's telling me, hey, we have a total of 2,392 rows. And in every single one of them, we have 15 columns. And it gives me a little bit of a head start there. And it gives me a little bit of the tail end as well. So head, it gives me 0 to 4. And for tail, it gives me from 87 to 91. So 5 rows from each side are being represented here. All right, so just like that, I was able to grab an entire data frame. I can see independent values if I really wanted to. I could see something like, hey, I only want to see, and you can see that it's already identifying for me what those possibilities are. Something like data.age, and it would just show the age if that's what I wanted to see. So now I'm able to read my data. Does anyone have any questions about how Pandas was able to interpret our CSV file and turn it into something like a data frame? Okay, no questions. I'm able to read my CSV file. Well, now I don't want my data to be thrown off by something like null values. Let's figure that out. I want to figure out what values are actually null. So I'm going to say data dot is null. I just want to see that information. I'm going to run that. And we can see that it's giving me false for a lot of my rows. And although this is useful because it's returning a true or false variable, it's not really useful in the essence that I actually need to find out which ones are true. I definitely don't want to iterate through 2,300 and something lines of rows of data and a bunch of columns as well. So there's got to be an easier way to do this. If I run .sum at the end of this and execute this, it tells me, hey, this is all of your student information, and not a single entry has a null value. So we need to worry about null values. Now, in the case that we did have no values, we would want to account for them by filling them in with the mean. The mean of that column. And we would do that utilizing the following line of code. We'll say, hey, data.fill all null values with the mean. And I want to do it in place. So we'll run in place equals true. Now this line of code, again, will be in case you have no values. Unfortunately, in this data set, we do not. All right. So now we were able to confirm there is no values. Well, there's still a little bit of a problem. Inside of these null values, or excuse me, inside of our data set, we know that there is a header named student ID. And we know that that student ID is going to have zero relationship to their actual grade class because it's just a serialized number that continues increasing as each entry comes in. So I'm not going to need that to be one of my significant features. Well, I could drop that. I could say, I could start dividing information by saying, hey, I have features, which my features are going, and I'm actually going to do this in a separate block so that it's not integrated there. So now we're going to determine features and targets. And we'll do that by saying, hey, in this line of code, I want my features to be my data set where I'm going to drop. And there it's asking me for labels. Okay, well, what I'm going to be dropping first will be the actual student ID. Oh, let me make sure that I remember what that column is called here. So it's just student ID. I'm just going to grab it like this so I don't do any sort of misspelling. That's the column that's going to be dropped in this representation of the data. And then I'm also going to specify, oh, that's it. I don't need to specify anything like the axis or anything like that. So now let's take a look at features and see what that looks like. So I'm getting a little bit of an error here. Oh, I do need that access portion. I apologize. All right, that's telling it how to determine once that student ID is dropped. So there we drop the student ID. We still have the same number of rows, but now we only have 14 columns. Now, I also want to drop my grade class because my grade class is my target, right? I don't want to include both of those together. So let me go ahead and draw this out here so that we understand what's happening. We have our total data file, which contains features. And also contains labels. Features being characteristics that can be utilized to determine the output. And labels, meaning the correct output for the given features. All right. What we're doing now is we're dividing them so that we have our features and our labels as their own separate data frames. And that way we can work with them individually. Let me see if this drop will allow me to drop more than one. Okay, looks like there's a drop multiple method. Let's try that one. Let's say drop. Nope, that's not how it works. We'll say features is equal to features dot drop. And in there, we'll pass in grade class. Axis of 1. And now we'll take a look at features. All right. Well, now our features have all of our information with the exclusion of both. We can see we only have 13 rows now. Now we don't have grade class or the student ID. And I see your hand up. Go ahead, Andy.
I was just wondering the difference between the data drop and the features dot drop. What's the difference here again?
Yeah. So data is referencing to the original data set. So the entire.
Oh, okay. I understand now. Sorry.
Oh, no, no problem at all. All right. So now we have our data frame and our features are ready to go. Our features have been determined. We know that we have 13 rows or 13 columns, excuse me. So that's going to be important later on when we start building our neural network. But now let's start working with our labels. In this block of code, what we do is determine our labels by saying, hey, the label here is going to be data, where the only thing that I need is my grade class. Now let's take a look at our CSV file. You'll see that in our CSV file, what we have here is 2.0, 1.0, and so on. Well, although all those are floating numbers, in reality, they can be represented as integers. And they actually need to be represented as integers in order for our data model to work correctly, because our model is going to try to determine which one of these classifications we're closest to. So we're going to take care of that here by adding a very simple I like to reference it as an interpreter here, where we can say as type and say integer. All right, I see a hand up. Go ahead, Carlos.
Is it supposed to be, is there a reason we're using data and not features?
Yeah, so these are going to be separate, right? What we want to access is we want to divide our entire data set. So this is the entire data frame here, or data, and we want to divide it so that we have features and our labels separate from one another. Right? So what we already took care of was our features. Now we're taking care of labels. Features meaning the characteristics, which is why we have 13 columns, whereas our label is just going to be one column of grade class.
Okay, I gotcha. Thank you.
Of course. All right, so now I go ahead and take a look at my labels here. Run that through. And we can see that our labels were able to come in just fine. We have all of our values all the way to the last row there of 2,392, which is what we expected, 2,392. So they both match. And we can see that all of our labels come in as an integer type. So now I have my labels and I have my features. Again, all of this is going to be utilized so that I can fit 13 features into my neural network. And for my neural network to then tell me, out of those 5 options, which one of them is the closest possible answer. All right. Well, now I have all of this data. But there is something called skewed data. So what do I mean by skewed data? The easiest way to represent this is, let's say we have, I'm a Mortarman, so I like to reference everything as left and right lateral limits. I'm sure there's a forward observer somewhere here that can relate. So let's say we have our bottom and top boundary. And as our data is being introduced into our model, or if we're plotting our data in a linear scalar way, maybe our data looks something like this. And ideally, our data would look something like this, staying between this top and bottom limits. That would be the ideal data flow. Unfortunately, data doesn't ever work like that. Instead, we have a very real possibility that as our data is coming in, what we're looking at here is something that will have a continuation, maybe it'll stabilize and flatline for a little bit, and then out of nowhere, just one specific data entry point will spike out, then we'll come back, then one specific data entry point will spike all the way up and then come back, and then maybe it doesn't come back and it stays up top, then drops to the bottom, right? And then maybe it just stabilizes towards the end, something like this. Now, everything within that top and bottom boundary, perfectly fine, because that's the information that we need, and it still allows our model to make accurate decisions, right? Our model is just essentially a machine learning ability where all these numbers or all this data is creating a pattern that can be recognized by the machine to make predictions. The problem comes with these skewed values. Here and here. So we need a way to standardize our data and fit our data so that these skewed values are corrected and cut off to ensure that our model can still make accurate predictions. Nick?
Why can't you just widen your limits?
Well, if I widen my limits, then that makes all of these entry points that are here towards the middle, and let me try to pick a different color here. It would make all these entry points that are here towards the middle have less of an impact.
So it makes the model less sensitive to the fluctuations in the center if you include the extreme outliers.
Exactly.
Okay.
Yeah. So in order to make sure that everything has the right amount of impact or the right amount of impression on my model, we want to make sure that everything follows this top and bottom boundary. Now, I could go out of my way to do a bunch of studies to figure out what my actual top and bottom boundary are and try to determine it on my own. But just like everything inside of programming, somebody figured out, hey, you know what? Everybody that works within the data science community is always trying to standardize their data and make it fit to a specific level. So maybe I should just create a tool that does this so that everybody can actually download it and use it with their data and standardize their data on their own. Well, that's actually provided to us here. This comes with scikit-learn or scikit-learn. And that's exactly what it does. It allows us to work with our data, figure out what the mean of our data is. It standardizes everything and squeezes it so that we don't have to worry about skewed values and that all of our data will have the correct impression on our data set, or excuse me, on our model. So we break them up into features and labels. Well, now we're going to feed both of our features and labels through this tunnel here to make sure that we're able to have, at the end of this, both balanced features and balanced labels. Or excuse me, I'm going to use the proper term here, call them scaled features and scaled labels. This way, I can actually train my model with some good working data. And actually, I apologize. I misled us a little bit. The only thing that's going to get standardized will be our features, not our labels. We don't want to transform or change our labels at all because those are our targets. So the only thing we need to worry about cleaning and ensuring that the data is not skewed is going to be our features, since that's what gives us our labels. All right. So now let's come back over. Let's work through standardizing and scaling our data to ensure our model is able to learn and recognize patterns without worrying about skewed data. Okay, so we're going to dive into our data frame one more time. And I'm actually going to install this information because I need access to the scikit-learn. And let me see where that command is. Okay, let me get that here. Go ahead, Andy.
I'm a little confused about what how big of an impact would skewed data be, if it's just, just out of the blue once or twice that happens. shouldn't the rhythm get back into like stabilized, I don't know, form? Um, typically shouldn't affect the output, right? I'm just a little confused of why we're so worried about it.
Well, when it comes to the way you're training data models, it's not necessarily that the model wouldn't be able to eventually adapt and give it information. You got to consider that the CSV file that we're currently working with is only 2,000 lines of it's only 2,000 lines of entries, right? It's not even 2,500 yet, which to us may sound like a lot, but for a model that's learning information for the very first time and trying to recognize pattern, that's nowhere near the right amount of data that it needs to actually just on its own anticipate skewed values and know how to disregard them and when not to disregard them, right? So since we're training the model with such a limited amount of data, we want to make sure that we do our part to ensure that the data that we're feeding to the model is as efficient as possible so it can learn properly. Does that answer your question, Andy?
Yeah, that makes sense. I thought maybe this was for a like an infinite type of model, but if it's finite data, it makes more sense.
Awesome. All right, so we're going to go ahead and pip install, and let me make sure that I see that correctly. It's going to be scikit-learn. And let me make sure I share that here as well. And now what I can do is say from sklearn dot preprocessing, I want to import standard scalar. And that standard scalar is what will actually allow me to scale my data. Well, how's it going to do that? Standard scalar, I see that it's in green and that there's a capital S. So that tells me that that's a class. Well, just like an OP, I need to create an instance of that class so I can utilize that tool. And now I actually have the ability to create some scaled features. By saying scalar dot fit and transform my features. So then I'm going to feed it all 13 rows. And then finally, I'll see my scale features. So now we can see that it's no longer a data frame that I'm working with. Now I'm working with a numpy array. So let me go ahead and clarify that. Returns a numpy array that can be interpreted as a tensor. All right. And we'll dive into tensors and everything that we're going to be utilizing this numpy array for during the second portion of our lecture. All right, so at this point, we're done pre-processing our data. We have some scale features that are falling within their left and right lateral limits. You can see their values have been alternated quite a little bit. We also have our labels, which are ready to go, all of our targets. So now in the part 2 of our lecture, what we're going to do is we're going to actually create a model and go through the training and evaluation process of this multi-classification model. All right, at this point, does anyone have any questions over this standard scalar or how we were able to break up our data into some scaled features and some labels? Perfect. If no one has any questions, let me go ahead and pause our recording here. All right. Excuse me. During part 1 of our lecture, we went ahead and scaled all of our features. We now have some nice standardized features, and we have our labels all set up and ready to go. Now, in that halfway portion, we took a look at a couple of videos that kind of broke down neural networks and the way it works. And now we're going to go ahead and actually talk about how we're going to enforce that within our file here. So here we go. In part 2, we're going to go ahead and actually train and evaluate our model. And our model will be created with PyTorch. All right. Now, in this portion, the first thing we will do is install PyTorch. We will talk about tensors. We will define a learning model. We will talk about linear layers. And we will talk about activation layers. We'll worry about back propagation here shortly. All right. So let's start off with actually creating our model. Or actually, let's start off with installing PyTorch. Well, what is PyTorch? PyTorch is a framework that's been created for learning models and creating learning models specifically with Python. So let me go ahead and send this here in our Avenger question so that we all have that available. All right, there you can see that PyTorch has been sent. Now, this framework allows us to build with very little code some pretty good and efficient learning models. Now, learning models, currently the ones that we're seeing, they've only been utilized with CSV data sets, but please note that learning models can also be utilized for some things like images or recognizing objects. So for example, Tesla's self-driving ability, part of its AI that's actually learning how to drive and identifying objects is built with PyTorch. Specifically for their cameras, they're taking pictures, and as soon as that picture is taken as the vehicle is driving, it gets rendered through the model, and the model tells the overall driving system what items they're looking at and how to recognize each portion of the information. Now, here in the installment process of PyTorch, we definitely want to do the stable version. You do not want to do the preview, which gets updated nightly. You can identify which one is your operating system and how you'll be going about installing it. Now, once I've taken a look at this and I have the information that I need, it's going to give me the install command down below. It tells me, hey, this is how you're going to install PyTorch into your machine. All right, now keep in mind, I am on a Mac, and that's the reason why this is the command that I'll be utilizing. But for you all, it is going to be dependent on your machine what the command is that you'll actually be utilizing. So now let's go ahead and pip install that PyTorch. Go ahead, Carlos.
Sorry, Whitworth. So I'm going through that part on PyTorch.org. And for compute platform, it's giving me CUDA, blah, 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 but different versions, and then CPU, whereas yours gave you a few other ones and then default.
So you're talking about these different CUDAs and then default?
Yeah. Yeah, you got default, I got CPU. Would it be CPU? I'm on Windows. Would it be CPU for me or?
If you're on Windows, then it would be CPU for you. Yes.
Okay, all right. This one, thank you.
Of course. All right. Now that I have it installed, I can go ahead and open up a code block here. And I can say excuse me, let me go ahead and take a look at these nodes here. I can import Torch. I can make sure that Torch is actually available by asking for its version. Gonna go ahead and run that. All right, so we see that that was successful. I get 4.9, so it worked. And I can go into the portion of building the model here. Well, now the question is, what is a model? We can go back into our TL draw. Our model is essentially just this layers of tensors here that we have been describing. We're going to go ahead and outline this so that we have an input layer, hidden layers, which is just a series of linear layers, and then an activation layer. And we'll go over the importance of every single one of them here shortly. Now, when we go into creating our model, we're also going to utilize something called linear and softmax. So we can look these up here. So PyTorch linear. All right, so this PyTorch linear portion, it looks like it gives two parameters, which is the in features and then the amount of out features. We can specify if we want to take off the bias. In this case, we will always have the bias on. And then it gives me a little bit of information as to the math that's happening under the hood in order for this tensor to work correctly and apply the linear layer to it. Now, linear layer. In this case, my input layer will be in linear layer. I will define how many tensors will come in, which in this case, it's the number of features that will be going into my model. I'll multiply it by 2 and slowly trickle down into my number of labels, which in this case, it's 5. So we know I have 13 features and 5 possibilities for a target. All right. Now, when we go into coding that, it will look like this. So first we'll start by making an OOP class. I'm going to import from PyTorch. I'm going to import it as N so that it's easily accessible to me. This N portion, that just stands for neural network. So in Torch, there's an NN module, which is all the neural network information that I'm going to need to actually make my model here. So what I'll do is I'll go ahead and say, hey, I have a class of a multi, let's just go ahead and call it student performance model. And the way I know this is going to be a model is by utilizing inheritance. I'll specify in N, there is a module. And that's what defines this as a model. Now, just like before, this is going to take in an initializer method. And it's also going to take in a function for accepting the forward pass. Thank you. We already are familiar with the forward pass from that series of videos, but just to break it down visually, the forward pass is the process of data feeding through a neural network or a model where it goes from the very first input layer to the secondary layer through all the hidden layers, and then finally hitting our activation layer. This entire process of feeding data down the model all the way to an output is called the forward pass. All right, so now let's go into defining our model. Just like I mentioned before, we are still going to need an initializer. So I'll go ahead and start that here. And I am utilizing inheritance. So because I'm utilizing inheritance, I can utilize the super method to activate the module. So in this case, I'm going to call my class itself. And then activate my init method. All right. This syntax is a little bit weird, and it's a little bit different than what we've seen so far. Before, what we saw was super.init, and we didn't have to define many of the stuff that's in here. In this case, we're just doing it more explicitly rather than implicitly like we did in regular OOP. But the same purpose is being achieved We're just making sure that both of these classes are being initialized properly when an instance of the student performance model is created. All right, now we can define a couple of variables. Before, we were taking in variables inside of my initializer, such as, hey, what's the name, what's the second name, and so on. In this case, I don't want to take in user input when I create a layer or when I create these classes. Instead, I just want to go straight into converting each layer. So for example, I can specify something called layer 1. And just to write this in shorthand, I'll do ly1, which will stand for layer. I'll make a little key here. So ly layer. So this is our input layer. In our drawing here, you can see that I had my number of features. And for the same number of features, have the same input. We talked that in PyTorch, what we're using here is going to be a linear layer that will take two parameters. One, the number of features in, and the number of features out. So now if I write this in code, I can say n.linear. And what would be the very first parameter here? If this is the number of features in,
13.
perfect. So we would define 13. And then after that, I would like to multiply it by 2. So I would say something like 26. But just to give me a little bit more complexity and availability, I'm going to go with 30. All right, this is completely user choice. You can experiment with how you want to decrement or increment your layers here. But this, as of right now, will do the trick for me. And then afterwards, I'll just start trickling down. I'll say self.layer2 will be n.linear. And I'll go from 30 to 25. After that, I'll go into layer 3, which will be linear, taking in 25 and outputting 20. And to repeat the process all the way into my final layer. Taking 20 and give me 15. Give me 15, turn that to 10. And self.linear 6. All right. So there you can see that there's going to be some sort of correlation, right? I received 13 features. My output is 30. So this passes out 30. Down below, I'm expecting to receive 30 neurons, but I'll hound out 25. And you can see that zigzag pattern kind of start happening here. So 30 comes down, 25 gets outputted, 25 comes down, 20 comes out is the output, 20 comes down, 15 becomes the output, 15 comes down, 10 becomes the output, 10 comes down, and 5 is the final output there. So there's that little zigzag pattern happening. All right, all I'm doing is I'm mimicking this forward pass. All right. Does anyone have any questions about this portion? Let's hear it, Andy.
I know you said like for the super we're being more explicit. I don't understand why you have student performance model in the super if it's supposed to reference the end module.
Got it. So the super portion, the keyword super, is what will actually reference the end module. So this portion here of super,
Okay.
that's what references the end module. That first parameter there is referencing to the model that I first created itself. That's why I mean that the syntax is a little confusing. This is still just referencing to the model itself, but the super is passing the model into N module.
Okay, that makes sense.
All right. Any other questions? All right. Well, now I have this 5 neurons. But here, in this example, we can see that even though I have the output, there's something else called the activation layer. And in the activation layer, something important must be happening there. Otherwise, it wouldn't be completely separated from the rest of my hidden layers or all my linear layers. Well, the activation layer is in charge of actually turning those 5 outputs into percentages. So I need a way to actually do that. And we'll be doing this action with softmax, which is the default activation layer for a multi-classification. So softmax will grab those outputs and give us a percentage as to what the likely answer will be. So there I do Control C. Let me, oh, excuse me. I did mean to send this to us. So that gives me access to softmax. And I can also grab it from the N module. I can say self.activation layer is equal to n.softmax. And in here, I'm just going to pass in that I'm passing a dimension of 1 because my target is in integer type. So I just need to pass in the dimension of 1. So there I've defined all of the different layers and my activation layer. So now I'm ready to actually make the forward pass. And I do so as such. Going to create a method named forward, which is going to take in neurons, or we'll just say features. N module is what tells it that we need to find a forward pass. So inside of the class of module, there is a requirement for the existence of a method named forward. If that method doesn't exist, then it won't know how to actually conduct the forward pass. Well, let's do that. Let's say output from layer 1 is equal to, and what we're going to go ahead and pass here, it will be self dot layer 1, where it takes in the features. Then we could say output from layer 2 will be layer 2, where what's being taken in is the output from layer 1. And we just repeat that zigzag pattern. We'll say output from layer 3 is equal to layer 3, where the input is the output from layer 2. Output from layer 4 will be layer 4, where the input is the output from layer 3. And continue on. The output from layer 5 will be the input from the output of layer 4. The output of layer 6 will be layer 6, where the input is the output of layer 5. And then finally, we'll have our result, which we'll call the activation function. And the activation function will take in the output from layer 6. And we'll finally return the result. Right? Now we're actually doing the forward pass of conducting the pass between each independent layer out through the activation layer. Now, you may be asking yourself, there's a lot of repeated syntax. Why am I writing this by hand when I could just utilize something like sequential? If anyone's familiar with machine learning, you know what sequential is. Well, being able to actually define the forward pass ourselves gives us more control to add optimization. And we'll start talking about optimization once we go into the evaluation and training phase here. Now, let's say I want to save myself some code, right? I want to save myself from writing this way too specific. Instead, the standard, or what you'll typically see, will be the definition of forward, which takes an x. Remember, x is just a variable of features. And then we just do variable reassignment, where x is equal to layer 1, or excuse me, self.layer 1. That takes an x. Then x is self.layer 2. That takes an x. Layer 3. Layer 4. Finally, layer 5. Oh, we have one more actually. Layer 6. And then we would return self.activation with x. Right? Exactly the same output or the same operation is happening. It's just rather than saying output from layer 1 and trying to be a little bit more descriptive as to what's happening, I'm just utilizing x as my consistent variable for my entire program. All right. Does anyone have any questions about defining your model and utilizing the forward pass? All right. If no one has any questions, then all we need to do is now that we've defined our model, we can make an instance of our model. So let's say learning, I could just call this, yeah, let's do learning model. And make that to the student performance model. So that will create an instance of our learning. I can run this. You can see that our learning model has been created. All right, we have officially built the model. Now that we've built the model, let's actually try to feed it one of our tensors and see what the output is. All right, let's take a look at our features. Excuse me, at our scaled features, because that's what we're actually going to feed it through. Okay, so that returns an array of arrays. Let's do scaled features at index 0. Let's count this out. 1, 2, 3, 4, 5. Well, that's 10 and 13. So there's my 13 features. Well, let's actually print that when we feed it through the model. Let's say learning model takes in our scaled features at index 0. All right, so it looks like we got a little bit of an error here. All right, and it's telling me that the input that I passed in needs to be a tensor, not a numpy array. And let me go ahead and grab that there. Oh, that's where that change happens. Let's see if I could do something like 2 tensor. Let me grab tensors here. All right, let's try to execute that block there. So tensor is not defined, and that's because I need to replay that block of code. All right, that works. Okay, now I get a different error here. mat1 and mat2 must have the same data type, but got double float. All right, I may have to do a little bit of moving around here. D-type torch 2. Okay.
Why can you just pass these scaled features into learning model like that?
Yeah, let me go ahead and answer that here shortly. All right, so my features, right, or my scaled features is just a numpy array for each one of the features. That numpy array holds all 13 of the characteristics that I want to pass into my learning model. So when I do learning model parentheses, this defaults to the forward pass or the forward method. So what I'm actually doing is I'm passing these 13 features, or excuse me, this numpy array that I'm turning into a tensor straight into the forward pass to make a prediction.
And because it's defaulted, you don't have to explicitly write forward parentheses.
Right.
Okay, that was where I was confused.
Awesome. All right, looks like we're still running into some errors. Dimensions out of range, expected to be in range, -1, but got 1. This is starting to turn into a little bit more of a hassle than I expected. We may have to go through the rest of the process of setting up our testing data first before we can even move into the seeing this feature portion. So let me go ahead and get rid of this block. I'm going to restart my shell here, or my kernel. And I'm going to run all to execute to make sure everything's nice and fresh. All right. Well, now that we have our information as far as our model, let's worry about creating our training data and our feature data. Splits. Well, we already have labels. This is marked down. Boom. Okay, we already have labels. And we have our scaled features. But they're currently not within a training split yet. Well, the way we turn this into a training split is by passing it through something called train test split. And that is also coming from sklearn. I'm going to come to the top of my file, and I'm going to import from sklearn model selection. I'm going to import train test split. This will generate a series of training and testing data. Now, why would I want something like training and testing data? So far, I have my skill features that already exist. And I have my labels that I really didn't change anything with. They're pretty much exactly the same as they were when they came in, except for the fact that I turn them into integer types. But now essentially what I'm saying that I want to do is I want to grab both of these and I want to divide them. I want to divide them in such a manner where 20% of this paired up data is utilized for testing. And 80% of this paired up data is utilized for training. Why would I want to do something like that? Why not use the entire data set?
So you keep them isolated from each other?
Okay, I could keep them isolated from each other, so if something goes wrong, I know where it went wrong. That's a good stab. What else?
Because they would already know the quote unquote answers to the training data, because that's what it's based off of.
Nice. So what we're saying is the model can remember information or recognize patterns, and what we can do is possibly overtrain the model and get fake results. If I'm taking the same test over and over and over again, the same exact order, the same exact multiple choice answers, and no matter how many times I fail it, I get to retake the test and it's exactly the same. Am I learning or am I just memorizing what the correct answer is? Right? At that point, I'm just memorizing. I'm not actually learning to recognize patterns or make accurate predictions. So in order to stop our model from being able to do that, from me being able to memorize and instead being able to learn, is we take away the ability to know what the test is during the training phase. And when we give it training data, we randomize it by a batch. And we also determine how big said batch is. So let's go into doing that. I have my training test split there. When I can define how this training test split is going to look. I have my labels and features that have already been created. And if I pass them into my train test split, I can go ahead and pass in my scaled features, pass in my labels, pass in the test size, and I can define that I want the test size to be of 20%. So if the test size is 20%, by default, I'll return a training size of 80%. And then finally, I can myself define how those randomized those randomized training data, how big that's going to be. In this case, I'll go with 42. This is kind of the standard value, 42 in test size. And it's a good place to start whenever you're training your data. And there you can see that it returns a series of 4 different NumPy arrays. Well, now I can divide those. Instead of putting them all in that train test split, this is just an array that holds, or excuse me, let me go ahead and put it this way. This is just an array that holds training data. Yeah, so it holds training features. It holds testing features. It holds training labels and testing labels, just as such. Well, this is the array and how it comes in. I can just destructure the array and grab it as such. Right? I'm just grabbing those 4 indexes that are being returned and giving them a variable value, destructuring that array. So now I can go ahead and take a look at both of them. I can just see training features. If I run this, I should see a series of NumPy arrays where every single one of them is 13. Okay, so that's great. I'm seeing that now I only have 1,913. Earlier, I had 2,300 and something else.
Is
Well,
that 80%?
this is the 80%. That's right. All right, this is the 80% of the data that I wanted. If I go to take a look at my testing features and I run this, I still see 13, but then the 20%, which is only 479 rows. All right, so I've successfully broken them up so that I have a training and testing set of data. But I still don't have a way to actually feed them to my model in itself. I'm going to fix this by actually changing the values, because currently right now what I have is NumPy arrays. And as we saw earlier, if I try to feed a NumPy array to my learning model, it throws an error. And it says, hey, wait a minute. What I expected to see here is a tensor from PyTorch. NumPy arrays and tensors are pretty similar. It's just that tensors are more of a PyTorch specific thing. And it also has a little bit more math capabilities than a NumPy array does. So let's fix it. All I'm going to do is utilize variable reassignment. You can say, hey, for my training features, I actually want to create a tensor where my tensor will take in the training features. And I want to change their data type to float 32. Excuse me, this is going to be torch. I'm going to do the same thing for my testing features. Again, I have a tensor that will take in my testing features. And the data type will be of torch.float 32. Now you may think, why am I defining this data type portion? If all of my NumPy array is already following some sort of pattern, what's the point of defining that it's a float 32? This is determining the level of accuracy that we want to go to. We could define it to be 64, we could define it to be 32, or even 16. 32 is the default for a good amount of accuracy. If you put 64, it will be accurate all the way out to the 64th decimal point, but it can also put a little bit more stress on your learning model from being able to make accurate predictions, and it may actually enable it to start doing memorization instead of learning. Also, if there's not enough space to actually fill in all the way to 64 integers, it'll start making up numbers to fill in all those 64 portions. All right, so there's our training features, our testing features. Now let's go ahead and do it with, and actually, let's just take a look at our training features now to see what they look like. So now we don't have a NumPy array. Instead, we have a multi-dimensional tensor. Awesome. Let's go ahead and do it to the rest, which is our training labels, which are training labels. I want them to turn into a tensor that will grab the original training label. And because these were integers, I want to actually turn this into a NumPy array. And after I turn them into a NumPy array, then I want to specify that what I want to churn them is not float 32, because again, these are integers. Instead, I want to utilize long, which long is whole numbers. And I could do that as well for my testing data information. So there's my testing labels. Again, we'll pass in our tensor. We'll throw in our testing labels. Say that I want them to go to numpy. And specify that the data type will be torch.long. All right, I'm going to run this to make sure it executes well. Awesome. And now I'm going to actually try to feed one of these through my model. I'm going to go through my training features and go to index 0. Make sure that runs. So that ran great. I actually have my training feature there. I'm going to pass it to my model. I'm going to say learning model. We'll take in my training features at index 0 to give it to the forward pass. Looks like we're still getting a problem here. So it comes from the activation function. Dimension out of range, expected to be in range, but got 1. Interesting. Might have done wrong when I defined my model. Let me make sure that I didn't do anything wrong there. And that's left max, dimension 1. Interesting. This doesn't work. We'll throw it into the data loader and then okay, so 1, 2, 3, 4, 5. Okay, 5 were given. All right, I'm gonna go ahead and keep pushing forward. We'll pass it into the data loader, and then from there, we'll go ahead and determine if there's a problem with the actual model itself. All right. Now, let's talk about a data loader. Currently, I have all of my data sets, but they're all divided. I haven't grouped them yet. My training features and my training labels are separate from one another. Although they were randomized in pairs. So row 0 of training features matches row 0 of training labels. But now I need to actually put them together so that they're able to work with one another. Well, from Torch, utils, data, I can actually import 2 things, a data loader and a tensor dataset. Now, the tensor dataset is utilized to group information. So let me go ahead and add this here. Grouping, feeding data. The tensor dataset is utilized to group training, or excuse me, group features and labels. So we broke them up. Now we're putting them back together. Now that we're done cleaning up all of the information, we're ready to actually start feeding it to our model. And then a data loader is utilized to feed the model. All right. Okay, let me go ahead and edit that. Boom. All right, so now let's work it out. First, we're going to actually create some tensor data. So here I'll say training data set. And I'm going to make that equal to our tensor data set. We'll pass in the training features and the training labels. Then I'll make a testing data set, which will take in the tensor data set which will be the testing features and testing labels. Let's run that to make sure that worked. All right. Now that we have our paired up information, all right, this is aligns features and labels. We can actually feed them into a data loader. So here I'll say training loader will be our data loader, which takes in our training data set. We can define the batch size that we're going to be feeding into the model every time. The default here will be 32. And I'll say that shuffle is true. I don't want my model to be learning, so every time I feed it a batch size of 32, I'm also going to ensure that it's not in the same order that it was fed in before. All right. Well, now I can do the same thing, bring it down, and instead of training, well, I know this is going to be my testing loader that takes in my testing data set with a batch size of 32. So now I have the tensor data and my training loader. All right. The next portion is going to be actually training the model. Before I move into that, does anyone have any questions over this training data set or what we've been doing as far as converting all of those tensors? Let's hear from Nick.
Would you display on the screen one of the two labels? I think from that block of code right there, either testing labels or training labels. Okay. That's just the grades, right? Zero.
No, this is the actual answer. So 4
Yeah,
would,
the final answer grade.
yes.
Gotcha. Okay. Was zero, I think 0 is an A, 1 is a B, 2, so on and so forth, or vice versa backwards.
Let me take a look. Da-da-da. Yeah, so 0 is A,
Perfect. Okay.
and 4 is F.
Okay. That's all I had.
Awesome. Any other questions? All right. If there aren't any other questions, then let's move into training our model. And this is where we actually apply our forward pass. So in order to train our model, like we saw inside of those videos, we have to actually define a way for the model to learn, meaning it needs to readjust its weights and biases to provide accurate predictions. And we need a way to find out how much to adjust by. So this is where our criterion and our optimizer comes in. Our optimizer is what readjusts our weights and biases, and our criterion is what tells us how much we need to adjust by. Right. So we do this. Both of these are going to be coming from Torch. I just need to import it from somewhere else. Okay. So it looks like from torch.optim, I need to import Atom, which is actually an optimizer here. And now I can start building my information. So I could say, hey, I have a criterion, which in this case, what we'll be utilizing will be cross entropy loss. And you utilize cross entropy loss for multi-classification models. And finally, our optimizer will be Atom. Now, this is going to help me find my optimal minimum. So readjusts weights and biases. And this is going to tell me by how much I need to readjust by. Now for Atom, I need to actually give it a little bit more information. I need to tell it what is it that it's adjusting, because it's readjusting weights and biases, right? Well, in my model, so I'm going to do my learning model. My learning model has a parameters method. That parameters method returns all the weights and biases at each linear layer. And finally, I can specify a learning rate of 0.001. That's just going to tell it, hey, how big of an adjustment do you want me to make every single time? All right, so cross entropy loss already defines how much of an adjustment we need to make. So if this says, hey, I need you to take 100 steps towards a direction, but my learning rate is of 0.001, it's going to say, well, I know you want me to take 100 steps, but I want to make sure that I don't go too far and miss the right information. This is your this is how much you want me to adjust from this batch of data. But instead of taking 100 steps, I'm going to take 10 towards that direction. And then when we make a new prediction of 32 batches and I recalculate this, well, this may still tell me, I want you to take 90 steps in that same direction. Or maybe he'll tell me, oh, you know what? From the last set of predictions that you've given me, I actually didn't need you to take 100 steps at all. Instead, I just need you to take 5 more steps in that direction. And that process continues into these two zero out, or are as close to zero as possible. Does anyone have any questions about that? Let's hear it, Andy.
Yeah, I'm wondering what's the purpose of criterion if we're going to take a specified amount of if we're going to specify how much we want them to take out of that criterion is something's not sinking in there.
Got it. So the way it looks like, if I were to look at this in a three-dimensional way, is not really three-dimensional, more of a two-dimensional, I guess. When the learning rate is happening, or as our model is learning, it makes predictions of those 32 batches. And of those 30, of those 32 batches, it may look something like this. Now, what Criterion is going to do is it's going to, by a flat increment, tell us this is how far I want you to move. But this is flat. It's not taking into account that there may be an incline or that there may be a decline. So even though what it's calculating is saying, hey, the right spot for us to stop, the golden place for us to be is right here. Well, let's say it tells me to take 10 steps. Great, I take 10 steps. After that, it tells me, all right, well, now take 10 steps again. Or it tells me, now I want you to take 30 steps. Well, when I take 30 steps, now my learning model has officially cleared the area where I want to reach. Right? It went too far. So in order to stop Criterion from being able to push us way too far, what we do is we take it in increments. We say, all right, well, I want you to take 30 steps, or we see that 30 steps there. And I say, all right, well, my learning rate will be at 0.01. So instead of taking those full 30 steps, I'm just going to stop right here. And then after that, it tells me, well, now I want you to take 50 steps. Okay, so we take in 50 steps, and we're at 0.01, so we're actually right here. And now it says, oh, you know what? You're right. I don't actually need 50 steps. I actually need you to take something a little bit shorter. Let's try something like 20 steps. All right, then it comes through and stops there. And then it says, well, now we're way far off. Let's try this again. And let's try to do something like 25 steps and meet halfway. But because we're at 0.01, we stop here. And it says, whoa, wait a minute. Now we're inside of a tunnel. Instead of going forward, I actually want you to go backwards a certain amount of steps. And because we're at 0.01, again, we end up closer and closer until we finally get to our goal mark. Does that kind of visualize it a little better, Andy?
Yeah, it makes sense.
All right. Okay, so there's our criteria on our cross entropy loss. Now let's actually get into the part where our model is actually making predictions, right? We went through this whole process of writing all this code, but we haven't made a single prediction yet. So let's go to that. I'm gonna start a loop iteration here. I'm actually gonna put my model, oh, hello. I'm gonna put my learning model into training mode. And in there I'll say for features and labels in my training loader, I want my optimizer, which in this case is Atom, to have a brand new bias, right? I don't want anything that was from the last 32 batches to carry over. That way it's always telling me a good amount of criterion there. So that's going to put it at 0 grad. And then I'm going to say, I want my output to be equal to my model. Features. I'm going to actually print that output just so we can see it. I'm not going to do anything regarding criterion or my optimizer just yet. I'm just going to feed it this portion. Okay, so we're getting that optimizer 0 grad. It's saying optimizer is not defined. I didn't execute that block of code. Okay, so now for those 32 batches, it was able to make predictions. Let me go ahead and do output at index 0 so that we could see it a little bit more clear. So 32 were fed in. Oh, it's because it's going 32 times, so it's printing 32 times. All right. So 32 separate results have been required for us. And for each one of them, here what we're seeing is the actual probability as to what our answer is. So as of right now, our model is saying, hey, the chances that it's index 0 is negative, or excuse me, that it's 4, it's negative. The answer that it's 3 is also negative. This is more likely a C because we also have negatives there, and there we can see 0.0609. So it's actually saying this is likely a C. We know that's not right. And our model right now has no way of learning because we haven't applied a way for it to do back propagation just yet. Where back propagation is the process where, hey, we feed it through the model up above, and we provide an answer or a prediction. But if that answer is wrong, what we do then is we tell it. We say, this isn't the answer. You missed the correct answer by this much. Let's just say that it's by 20. Well, then it goes backwards and it says, why did you miss it by 20? Well, I missed it by 20 because this guy, this layer, told me the following. Well, why did you tell him that? Well, I told him that because this layer told me this. All right. And why did you tell him that? Because this layer told me that. And then finally, we get to the root source, so that first linear layer, and we tell it, okay, this is where you messed up. I need you to fix that information so that next time you relay it forward, we can fix weights and biases at every layer. So that's the process of backpropagation. We're fixing each layer's weights and biases from the result. Well, let's do that now. We have our output. We can calculate our loss, so how much we missed it by providing our criterion, which is atom, giving it the output results, and our label. What was the correct answer? Then by saying loss.backward, this is what gives my bottle the ability to learn. It's providing the back propagation step. And then finally, my optimizer, because it's learning and it made a prediction and told me, hey, this is how far you're off by, can finally take a step forward. Right? In that drawing that I made earlier, each one of these green lines is my step forward. All right. Well, now let's go ahead and take this model and run it through again. And then we'll take a look at the calculation between our running loss there. Okay, so we can see these numbers are starting to become a little bit more complex when they're being printed out. The propagation is happening. We know it is because it's telling me, hey, the atom did a backward step. So this is working pretty well so far. If I were to match it to an actual answer, which we will here shortly, let's actually start calculating our running loss. I'm going to go ahead and say I'm going to grab some epochs, which is a training iteration. I'm just going to put it in range of 20. I want this training iteration to happen 20 times. I'm going to calculate how much is my running loss. So how inaccurate is my model? After every iteration, I will add my loss to it. And I could do that by grabbing that item within loss. And then I'm going to calculate what the average loss was for that training iteration. So I'll say average loss is equal to running loss divided by the length of the training loader. And then finally, I'll just add a little print statement so I could actually see it. I'll say if epoch plus 1 is not something that can be divided by 10, then I want to print my average loss. And then I can actually print the epoch. All right, we run this. Oh, I forgot to remove that other print statement that I had earlier. Did I? I did not. Did I miss a print statement? No. Why is it showing me that tensor? All right. So it looks like my average loss was of 1.02 as of now. So I expect it to just get lower every time. I'm actually going to restart my kernel because I'm getting a little bit of misbehavior. I don't think I have a missing print statement. I'm going to execute all. Oh, that's happening because I put a print statement somewhere else, didn't I? Probably within my model. I did. Okay, so now I just see my average loss. So at epoch 10, it was at 1.05. And at the final epoch, epoch 20, it was at 1.03. So my model's learning. My amount of loss is going down every single time. Well, now the question is, how accurate is it? Let's go into the evaluation portion. So from Torch Metrics, which I need to install actually. All right, so now say from Torch Metrics, I want to import accuracy. I'll make accuracy where I can specify the task, which in this case is multi-classification. And I can tell it that the number of classes is 5. Well, now I can put my model into evaluation mode. Earlier, I had it in training mode. Now I put it back into evaluation mode. I can specify that I want Torch to carry no gradient in this case, because I'm not going to be adjusting my model. And same thing like before, you can say 4 features and labels in my testing loader. I can grab my output, which is my learning model, taken in the features. I can create a prediction, so I can see the predicted factor here. And I'm going to grab the max value out of that torch. And flatten it to closest to 1. And then I'm going to update my accuracy, where I'm going to pass in the predicted and the labels. Let's actually take a look at what predicted looks like. And at the end of this iteration, well, now I could just print my accuracy. I apologize, everyone. I know the syntax is probably a little bit foreign to us, and I'm kind of speeding through this last portion because we're running out of time. I'm going to go ahead and restart my kernel, run all. You can see that it got to my training portion of the epochs. And then it got to the evaluation. So there you can see this is my output. So it said, hey, this is 444. Well, the actual answers is 434. So my accuracy isn't the best just yet. And you can see that my model is already at 77% accuracy. All right, so my model can make accurate predictions from what I was able to give it to 70% of accuracy. It compares the truth to, or excuse me, it compares the prediction to the truth. Now, quick ways of fixing this is you could increase the number of epochs you put it through. You can make it all the way to 200, and that could increase your actual how accurate your model could be. And you could also add a concept of ReLU, which is similar to a linear layer. It just has the ability to stop it from going flattening out to 0. So that way each linear layer is always having an effect on the next one. And you could also change it, say, so just by changing it to 200 iterations of epochs, now it's 84% accurate instead of just 77, right? And you could also add something called dropout layers, where at random, while the model is being trained, the model will randomly cross out some linear layers so that there's no codependency on one specific layer. And by randomly getting in of each neuron, not a layer, I apologize, it's able to make better connections within the neurons that aren't being canceled out. So things to explore there are going to be dropout layers and the ReLU function. All right, everyone. Does anyone have any questions regarding learning models, how we were able to pre-process our data and actually run our data through a training and accuracy iteration? Let's hear it, Nick.
Is there a way to see which of the inputs or how much they affect the output? Like, for example, how much age made a difference in the outputs? Because this is on that student data where there were ages from like 16 to 18, I think it was, right?
Mm-hmm.
Is there a way to isolate if that made any difference at all, or if it didn't matter?
It's called a relational map, what you're talking about. We're not going to be able to cover it in this class, but it is a data science concept where before you even go through the process of training the model, you would build a map where essentially through plotting all the information, you would be able to see how each one of these columns relates to the output.
So, and that's before you even get into training the model.
That's correct.
Okay.
Any other questions? Okay, awesome. If there aren't any other questions, I'm going to go ahead and stop our recording here.